Message passing can be done with basically independent computers that communicate via a network. Communication is via explicit I/O. That means that if we're sending a message, we're explicitly saying, I want to send this information to this other process running on this other computer. And a program can't access the address space of the other process. All it can do is send messages back and forth. The advantage of message passing machines is that it's easier to build them and they're more scalable than shared memory machines because you don't have to have communication at such a fine grain. But it further removes the programming model from basic hardware operations. We want to look at this little diagram down here where it shows what's going on when you send a message. So basically, the send primitive and the receive primitive both have two parameters. The send primitive specifies a buffer to be transmitted, let's say X, and that's the location from which the value is sent. And then it also specifies a receiver process, in this case Q. The receive primitive, on the other hand, specifies the location in which to put the information that's received, that's Y, and a process from which to receive it, that's P. So what that does when the send takes place is to transfer information from the address space of process P at address X to process Q at address Y. Now, this is the basic idea of a send operation, but there are a lot of variants that have to do with when certain actions take place. There is a possibility that send will complete when the receive has been executed. Now, what that means is if process Q is behind and it's not to the location yet where it does the receive, process P has to wait until the receive gets done. It's also possible that the send completes when the send buffer is available for reuse. So that means that as soon as we've gotten the information out of the send buffer and sent it across the network, then the send completes. Or it's also possible that as soon as the message has been sent, the send completes. So in this case, we might have multiple buffers, and as soon as we execute the send operation, we can proceed. The program that did the send can proceed immediately. So these have different terminology depending upon whether the send the receive occurs as soon as the receiving process gets to that point, in which case it's called synchronous, or if the send completes as soon as the message has been sent, then it's called asynchronous. Now, this sounds simple, but there are a lot of overheads. Let's describe each of the overheads. First of all, we have to do a copy, and this means it takes longer than it does on an SAS machine. Why is that? Well, we have to copy more than once. Instead of being written to memory once, information needs to be written to local memory of one process and then copied across a network to another memory. So not only are you writing it twice, but you've also got this explicit transfer across the network that occurs in between. Now, you also need to keep track of whether information is still in the buffer or it's been copied from the buffer, which means that you could then reuse the buffer portion for another message. So a set of unused buffers has to be tracked, or you have to maintain queues of information waiting to go out. You also have a protection problem, and that is that one process cannot be allowed to access another process's memory. And that means that if you're doing a send, it's got to be the operating system that does the send, and that requires a context switch. So the operating system needs to be involved, and context switches take typically several hundred instruction times, so it's really expensive to do a send relative to communicating with shared memory. I want to give an example of the difference, and this comes straight out of the book, the difference between parallel programming using the shared address space model and the message passing model. So let's see if we can fit both of these on the screen, as we have right here. The shared address space model, you see, has two processes. One of them is just created here. When we do the clone of a process, that spawns a child thread, and the child thread executes the doSum method. Well, the doSum method waits while this shared variable signal is 0, and then at that point it goes ahead and does the print, And what it does is to print the sum of two values, to sum of two variables there. And then it sets the signal variable back to 0, which signals the parent process to complete. So the way the main process works here, the main thread, is that it starts up the child thread, and then it sets signal to 1, which tells the child thread that it's okay to work, because the child thread is looping until signal becomes something other than 0. That allows it to go ahead. And now it gets in a while loop, waits while the signal value is 1, which means until the child thread is finished with the addition and printing. And then after the child is finished, then it can hop out of the loop and then print all done exiting. Okay? Message passing, on the other hand, does things a little bit differently. It forks a process. It says the main process starts up. If fork equals 0, that is, if it's the child process, then it does sum. Now, if fork is not equal to 0, it means it's the parent process, and in that case, it sets A to 5 and B to 3, and then sends a message to the child that tells it to the two values to add. The child then goes ahead and does the receive and prints the value. And then after it waits for the child, it can print all done exiting, and then we're done. And I just copied a little on the fork documentation to show you what's going on here. A fork is set to 0 if it's a child process. But if it's the parent process that actually executed the fork at first, then the fork is going to return the process ID of the child process. So when we test for whether it returns 0, we just check to see whether it's the child process. And in that case, we execute that doSum method. Otherwise, we initialize the two values, send a message, and wait for the child process to finish. Okay? So those are examples of message passing and shared memory programming.